Right, good evening. Good evening, everybody. Thank you for joining us in this first one in the academic year's inaugural lecture series. I'm Nicholas Braithwaite. I'm the Executive Dean of the Faculty of Science, Technology, Engineering and Mathematics. And I'm proud and privileged to be hosting one of our inaugural lectures here. And the series showcases our research, teaching and knowledge exchange portfolios. I'm also delighted that we can deliver this one here on campus in a COVID-compliant way, of course. And it's been so long since we've been in this room doing this sort of thing. Very exciting. Now, each year, the Vice-Chancellor invites some of the recently appointed professors to give an inaugural lecture. Over the course of a year, our series provides an opportunity to celebrate academic excellence, with each lecture representing a significant milestone in an academic's career. But before we get a long way into that, let me just do the housekeeping bit. The lecture will be followed by a Q&A session, and then we'll invite you to celebrate, if you're in the room here, celebrate with us downstairs, and we ask that you follow the exit signs and go that way to leave the theatre. During the presentation here, for those in the room or those more remote, it'll be easier for you to do it, I guess. If you want to use Twitter to increase the exposure we get, that would be appreciated. There's a hashtag displayed up there, and we also like you to tag it with @OpenUniversity, and that lets the world join in. For members who are watching, colleagues who are watching via the live stream, for your questions, please email them. If you keep it succinct, it will help because they're going to be relayed to me by somebody reading the email out, and then I will relay it to Stephen. The purpose of that is to give him some thinking time, but not too much. Okay, so let's talk a little bit about my colleague, my esteemed colleague, Stephen Lewis, Professor of Atmospheric Physics at the Open University. He's currently head of the School of Physical Sciences, and he researches into the dynamics of planetary atmospheres. Now, I want to go back a little bit on this and say that what he's doing is really important in understanding the weather on other planets, and he's going to challenge us with why that might be important for understanding our own weather and climate better. And I know firsthand that he does understand the weather on this planet, as we worked together with a colleague, Sheila Ross, on a course that was essentially of that name, Understanding the Weather. Stephen joined us, and it was shortly after he joined us that I lured him into that because I found out he was a meteorologist at heart. He joined us in 2005 as a research fellow, and by 2009 he had advanced to senior research fellow, 2010 transferred over to being a senior lecturer, and by 2017 professor of atmospheric physics. Now, his understanding includes the dynamics of climate systems, that's why it's part of the title, and forecasting the weather for spacecraft missions and interpreting the atmospheric observations that they return is really important. In fact, it's as important to space exploration as the early forecasts were on Earth for exploration of all types, by land, by sea, and particularly by air. He's won awards for his work on spacecraft teams, including NASA Mars Reconnaissance Orbiter missions and the Curiosity and Perseverance rover rovers. I'd run out of words. Back on Earth, it's important to note that he is a fellow of the Royal Meteorological Society, and in that course that we produced together, he was very effective in linking us up with that organisation. He's been the academic consultant, as you would expect, on a number of BBC series. Wild Weather, that would be one of his, and A Perfect Planet. And that's a perfect point for me to pause and introduce tonight's speaker, Professor Stephen Lewis.
Thank you, Nick, and good evening, everyone. So I was asked to give an inaugural, and I'd already given a talk recently about the planets, and so I thought, what could I do that was a little bit different? And I'd really like to theme this around, what can other planets tell us about the Earth? This is, of course, a view of the Earth's atmosphere, but it's a view from space. It's actually been taken by an astronaut on the International Space Station, and it's a view of sunset, and you can see the various layers of the atmosphere. The weather that we're accustomed to is all in the lowest part, below the bright below the bright line where you can see the clouds, and then the middle and upper atmosphere above the stratosphere and mesosphere. So that's the Earth. What about other planets in the solar system anyway? Well, almost all planets have an atmosphere. It's arguable whether Mercury does, but all the other planets have a significant atmosphere, and these are our two neighbours, Venus, Earth and Mars, from left to right. I don't know why that's gone forward without me touching it. You can see that each of them are dominated by atmospheres to different degrees. Venus completely covered with clouds, Earth a mixture of clouds and some land, and Mars only very thin cirrus clouds. And these planets have suffered different fates, but really the differences in surface conditions on each planet are much more due to the atmosphere than to anything else. Venus, well known for a runaway greenhouse effect and temperatures hot enough to melt lead. Mars, essentially a frozen desert. They're certainly not the only atmospheres. In fact, not most of the atmosphere. This is an image of Neptune. It's an image I'm rather fond of, actually, because it was actually the last planetary picture, just about, taken by the Voyager 2 spacecraft as it flew out of the solar system back in the late 80s. I think 1989 was it? It was the late 80s, and I was actually in California at the time this image was taken. It's the first time I was involved in a NASA event in which a spacecraft flew past the planet. So the last of Voyager from the grand tour of the 1970s, and the first space mission I was involved in. Beautiful blue planet with some streaks of white cloud just visible above, and the great dark spot which is no longer there in the centre of the image. Moving on to another planet. This is Jupiter. When it comes down to it, it's the biggest atmosphere of them all. It is basically all atmosphere down to a level at which the physics becomes rather strange when we enter metallic hydrogen-dominated region. This is a view of Jupiter we didn't have in my day anyway. When I was first a research student, this is an image from the NASA Juno spacecraft, which is operating now, and it's actually a view down over Jupiter's north pole. So until recently, we'd never seen the poles of Jupiter because, of course, from a telescope, we tend to see the equator rather well, and the poles are very foreshortened. And the same from the Voyager spacecraft simply flew by in the plane of the ecliptic, the plane where all the planets orbit the sun. But you can see that Jupiter's atmosphere is just a fantastic fluid dynamics playground. If you're into fluid dynamics, this is the place to go. It's full of whirls and vortices, very active systems, all the time thrashing around. In fact, the particular vortex I started my PhD on is this one. This is a more recent image, but it's a nice image of Jupiter's famous Great Red Spot. This is a vast vortex. You could fit at least 2 Earths within it, so that gives you an idea of the scale we're talking about. The vortex rotates every few days. The gas whirls all around the outside. And the other kind of interesting thing about it is that it's been there for a very long time. It's changed in size and colour a little bit, but it's a little controversial who first saw it, but there's certainly a record of Robert Hooke seeing it in 1664, because he wrote it up in the first field trans of the Royal Society. So we know that he saw it. It's likely, although it's not clear, that Cassini, the Italian astronomer who was operating in Paris at the time, also saw it, and it's a little unclear who saw it first, but that doesn't really matter. The point is they both saw it, and the reason why it was first seen at that time was not because it formed then, probably, but because telescopes were just being invented that were good enough to see it with. So this is a fantastic feature. It's often described as a hurricane, or you will see it said it's to be like a hurricane. It's nothing whatsoever like a hurricane, actually. It's completely the opposite. It's actually a high-pressure system, an anticyclone. It's in the southern hemisphere, which is why it's rotating the way it is. And it does have I did my research on the dynamics of this feature, and it does have an analogue in Earth, and the Earth analogue is actually a blocking high, a very stable, high-pressure weather system. And famously, the winter of 1963 was a particularly bad winter, a good year otherwise, I might point out, but it was a bad winter. And the reason why was because a blocking high like this was sitting over the country just holding that cold weather, and lasted for about a month, which is a long time for Earth weather. well, this feature has clearly been here for 400 years or getting on for that, plus we don't know when it formed. So an amazingly long-lived feature. Over to a much smaller planet now, but to show another atmosphere in action. This is Mars. This is the North Pole of Mars. I'm sticking to polar pictures for now. So this is a beautiful view of the North Pole of Mars. The ice cap you can see on the right-hand side of the image is essentially a water ice cap. And people will often think of Mars as this dry, dusty desert, which is true to a large extent. But look at the active water cycle going on here. There's water ice on the surface in the polar cap. More towards the centre of the image, this huge bank of cloud here. This is stratocumulus cloud. If you've done understanding the weather, you might recognise that. It's quite unusual to see so much stratocumulus cloud on Mars, but this is stratocumulus cloud. And then further down over to the left, we're going towards the equator, and there's fogs actually and thin cirrus cloud. So these are all water ice clouds. So there's an active water cycle going on even on reputedly the driest of dry planets. So plenty of atmospheric excitement going on there as well. And I'll produce some examples from Mars later in the talk. So as Nick mentioned, one of the most interesting or most different parts of my job at the OU has always been to work as an academic consultant on various co-productions with the BBC. And a natural one that happened recently in 2019 was The Planets with Brian Cox. And I was involved in a lot of the science of this. You may have the poster. So it was natural that I was involved in that. But more recently, actually over a long period of time, but the programme was finally shown this year, A Perfect Planet with David Attenborough, which you may notice doesn't involve a lot of other planets. It involves a lot of animals and the Earth. And yet I worked on this series, and I can remember vividly, I was sitting at home working through some scripts or looking at some images on my computer, and with the respect and deference that my children have always given me, one of my daughters came in and said, "Well, what do you know about that?" And so that's the motive for this talk, really. What do I know about this? Why do they put a planetary scientist on a programme about the Earth? Well, here's the Earth's atmosphere. This is space is nearer than you think, I always like to say. You would get a view not unlike this if you travelled about the same distance as you would travel to London from here upwards. It's not very far away at all. This is obviously a view from the International Space Station, so the actual photograph's been taken from higher up, but you can see a Soyuz capsule approaching in the lower part of the image. But all the weather you can see going on down here is all within a few kilometres of the surface. The tops of these clouds are all well below 10 kilometres. So a rather sobering thought, perhaps, is that all the life that we know about in the entire universe exists within a layer of a few kilometres of the surface of this planet at the moment. We're really living in the thinnest of shells around the Earth. If the Earth was an apple, it would be thinner than the skin of an apple, and that's the only place where we know life exists. So it's quite a precarious position to be in, perhaps, in some ways. And that brings me on to how do we study the Earth's atmosphere? Well, what a scientist would normally like to do, like me, if you want to study a fluid system, well, you go into the laboratory and you spin it faster, or you heat it up a bit more, or you do something to it and change the parameters and see what happens. Probably a bad idea if you've only got one atmosphere to live in. So I'd like to talk a little bit about how we study the Earth and why other planets might help with that study. Well, two ways we could do experiments in atmospheric science is we have to look at different systems that we can do experiments without affecting the real thing, hopefully. So just two examples I've worked on here in sketch form anyway. On the left, a rotating tank experiment. This is you probably don't get an idea of the scale. This is actually an EU facility in Grenoble that I've done some experiments on, and this is a 14-metre rotating turntable, several metres deep. If I can just point to, you may see there's some computer screens up here. You can walk along this plank here, and several people can sit on this plank when it's operating. It operates in the dark because the only way we can find out what the fluid is doing is by shooting sheets of lasers at different heights in the tank. This is an example of one in the lower left, and then we use essentially clever video tracking technology to track the motions. And the reason why it's still valuable to do experiments with actual real fluids is that we can access a range of scales that you just can't access in a computer simulation at the moment, even. We have a tank that's 14 metres across, but fluids move on scales of millimetres. And so we can access that whole range of scales and range of motions. The other side of the slide is actually what I'm going to talk about much more tonight, because it's more commonly done for the planets I'm going to talk about, is a giant numerical model. Now, the way we model an atmosphere is that we effectively split it up into lots of little boxes. At least this is conceptually what happens. It may not actually happen according to the precise technique used, but effectively we divide the atmosphere up into a whole bunch of boxes, both in the horizontal and in the vertical, stacks of boxes in the vertical, and then we solve the various equations we want to solve for each box. And so the more boxes you can have, if you like, the more resolution you've got. It's a bit like having a HD TV rather than the old-fashioned conventional TV. We can go to a higher resolution with a bigger computer, and we can make something that hopefully looks more like an atmosphere. The trouble is, atmospheres are rather complicated, and I've got to put a lot of different equations into each box. And here's just a few of them, really. There will be a test on the equations on the top right at the end before you get your glass of wine. Effectively, though, it's not that. I'm joking slightly, but I don't really expect you to follow all the bits. But the point is that there's lots of different science. In fact, these might be rather better called kitchen sink models than global. They're called global circulation models. But we effectively have to throw in everything that we think is important. And it turns out that a lot of things are important. So the first three items are kind of the equations of fluid dynamics. This is just Newton's second law, written in a slightly unfamiliar form because you're in a rotating frame of reference on a planet. And that's why there's some extra terms there. And there's gravity to worry about. And there's other things going on. But it's Newton's second law. It's acceleration equals force divided by mass. We then have some other, so the good old classical physics, really. Continuity and equation of state, we need to understand. So continuity basically says mass is conserved. The equation of state describes, we're describing a gas. We could equally well put in a different equation of state if we were describing a liquid, an ocean. Then we've got the law of thermodynamics, effectively conservation of energy. There's a little term here that looks rather innocent, which is the Q on the right-hand side of this. Whenever a physicist write a scripty letter, that often means there's something quite dark and deep buried there. And in this case, it's basically everything else I'm going to talk about, and it's about 90% of the computer time involved in solving these equations for the boxes, what goes on in the Q, to calculate what Q is. So, for example, we need to know about radiative transfer at different wavelengths. We need to understand about sunlight coming in, infrared radiation going out, the scattering of both, the absorption of both. There's cloud and ice physics. You've seen some clouds and ice. We need to know about how things condense, sublime, precipitate. We need to worry about the surface. So we need to talk to some geologists and geomorphologists because we need to know the shape of the surface and we need to know the properties of the surface and how heat is transferred from the surface to the atmosphere. If we were on the Earth, we'd need to know about the ocean as well. Then there's aerosol physics, hugely important particles from volcanoes or from dust storms. And then atmospheric photochemistry. So chemistry turns out to be a huge time hog on these models because we have to track instead of just tracking a gas, we track every species that we think is important, and then we make them all react in the boxes. So we have to talk to chemists. And then we need, sometimes, if you're working on the Earth, you talk to biologists. And sometimes even some people will even put in economics models in, all sorts of things. So the point is that it's not just, although my speciality, if you like, are the top three lines, that I need to talk to lots of other people. It's a huge collaborative effort. Virtually the whole of STEM science and some people from outside STEM are involved in formulating parts of these models. So it's an interesting exercise. So next I thought I'd talk a little bit about weather and climate because there's always some confusion between the two. And there's a rather infamous quote, climate is what we expect, weather is what we get, which to some extent tells you something about what's going on. often attributed to Mark Twain, although it's not, that apparently is not correct. And then it's since been attributed to Robert Heinlein in the 1950s, but I don't think that's right either, because there's records of it being coming from America. Came from some book of American student answers to exams or something from the early 20th century. So we don't know really where it comes from, but it's perhaps sums up the point. So individual weather events are how the atmosphere changes from day to day. Why is today different from yesterday? And why will tomorrow be different again? That's weather, if you like. And actually, we can predict these with large numerical models of the type I've described. And surprisingly, our skill is actually getting better. You may not believe it, but our weather forecasts are about a day better every decade. There's a sort of rule of thumb. So what that means is that a weather forecast now for 5 days ahead is as accurate or as skillful as a weather forecast was 3 days ahead 20 years ago. And the main reason for that is actually there's a combination of reasons. Partly the models, and partly the fact that we've got better observations. We've got more satellites, and so we know more about what the atmosphere is like now. Climate, on the other hand, is a sort of average. You can think of it as an average, perhaps on a decadal timescale, formerly on a 30-year timescale, although often the 10-year climates are published. And it's also about the pattern of variations about that average. So if we're thinking 10 or 30 years ahead, the question I'm sometimes asked is, well, you can only predict the weather a week ahead. How do you know anything about climate 10 or 20 years ahead? And the answer, it actually sort of stems from something that one of the members of my family was fond of saying when I was younger, which is, you never meet a poor bookie. And that's essentially the answer here. So you can think of it, this is a rather simple-minded analogy, but you can think of it this way. I believe that there are games in which people wager money, which involves throwing 2 dice, and it's something to do with the score you get. So if I threw 2 dice, and you ask me, what will the score be next time you throw them? That's an incredibly difficult problem, actually. On the other hand, if you ask me, what would you expect the score to be, I can solve that rather easily in my head. So to give you an example, let's say is this going to go ahead? So we could think of predicting what's going to happen next time as a weather forecast. It would actually be very hard, but there's nothing fundamental that would stop you from doing this. You just need to know exactly where the dice were at the start of the throw, exactly what orientation they were in, exactly what velocity they were moving with, and you'd need to know all about the material properties of the dice, the material properties of the surface they were going to hit, the air, and you could throw a massive supercomputer calculation at this. And in principle, you could try to work out what those dice were going to land on. I have to say, I think it would be very, very difficult. It would require vast resources, and it would also be very subject to tiny uncertainties in the initial conditions of the dice, because they're going to bounce and collide, and a lot of things will happen. So you can think of that a bit like an analogy for weather forecast, probably even harder. This is a really quite a hard problem. You'd have to throw a lot of physics at it. On the other hand, if you ask me what you would expect the score to be, well, assuming the dice aren't biased, of course, I know that there's 36 possible answers, and 6 of them are going to be 7. So a sixth of the time, I expect to get 7 as the total. That's the climate. And equally, there's a distribution, and I'm progressively less likely to get numbers that are different from 7 until I get to 2 or 12, which are both going to happen one time in 36. So I can actually very easily describe the climate. And you might even think that you could push this analogy a bit further. I don't want to push it too far, that we could bias, if we started to bias the dice a little bit, that might be climate change. So why do we get weather anyway? What's going on? This is a sort of simplified picture of the Earth, but it could be any planet, actually. A beam of sunlight hitting somewhere near the equator falls on less surface area than it would do if it hits at higher latitudes. And effectively, what happens is that the tropics, on average, day and night, over the year, absorb 300 watts per square metre from the sunlight. But they actually only emit 250 watts per square metre. And in contrast, the poles absorb 50 watts per square metre, but emit 150 watts per square metre. So what's going on? Well, clearly the energy isn't being isn't being created or destroyed. What's happening is that the atmosphere and the oceans, to some extent on Earth, is transporting the heat from the equator to the poles. And in classical thermodynamics, which was a lot of which came about in the 19th century, for reasons not unconnected probably with the Industrial Revolution, this is called a heat engine. You can think of it, engines move because often, certain types of engines move because you heat parts of them to hotter temperatures than other parts, and they move in response. And effectively, that's what the atmosphere is doing as well. And you might wonder, how powerful an engine is it? Typically, the Earth's atmosphere, which is not a particularly big atmosphere, is about a 5 petawatt heat engine. Now, that's quite a hard number to visualise. So I've tried to break it down for you. 5 petawatts is 5 with 15 zeros after it. And I tried to think of the biggest sort of mechanical engine that I could think of. And imagine the space shuttle, just after it's lifted off, the space shuttle with all its boosters firing at maximum as it tries to accelerate away from the launch pad. You would need 500,000 of those to get to 5 petawatts, all on maximum thrust. Well, another way of thinking about it is, what's the peak electricity consumption of Great Britain? Well, actually, the most ever recorded, which was recorded in winter 2 years ago on a cold day, was about 100,000 times less than this. So it's a vast amount of power. More loosely, somebody's tried to estimate the total power consumption in all forms of the human world. So everything we do, oil, coal, wood, electricity, all added up, and it's still 25 times less than this steam engine that's cranking on above our heads right now. So weather is pretty powerful. So how does the atmosphere actually move? Well, this is a classic figure from our Understanding the Weather book, actually, from the AU. It's a chap called Hadley explained the tropical circulation as large cells, and these are the blue cells near the equator here. So rising motion at the equator and then falling motion away from the equator. And the reason why he was interested in these was this was the 18th century, and he was interested in the trade winds. He's trying to explain the trade winds. And effectively, it's not exactly what happens, but it's a good picture to have in your mind. But then about 100 years later, a bit more, in the 19th century, an American meteorologist called William Ferrell suggested, well, there must be some other cells rotating the other way to carry the heat onto the poles, because we know the poles are emitting about 3 times as much heat as they're receiving. The poles would be a lot colder if we didn't have an atmosphere. We've drawn these in purple. You will often still see them to this day in books and all over the internet, Ferrell cells. There's a small problem with Ferrell cells, which is that they're not actually there if you go and look. There's nothing like that happening. Well, there is something like that happening, but it's only like that in the average sense. What actually happens is that the motion breaks down. It's not this simple sort of two-dimensional overturning circulation like a cell. It actually breaks down into wave-like motions. And we're familiar with these, actually, because when the peaks and crests of the waves pass over us, we say we're having a high or a low-pressure system. And this is exactly the weather that's passing over us right now, actually. We're in a low. Not a very strong low, but a low nonetheless. So the motion up here is not this Ferrell cell at all. So if you ever see that picture, view it with a pinch of salt or colour it purple as we did, and try to remember that actually what's going on here is waves. So let's look at a real picture of the Earth. And this is an image of the Earth from February, actually, from a satellite that's actually, just for convenience, sitting right over the equator and right over the prime meridian, so right over the Greenwich meridian and right over the equator. And you can see the effect, the Hadley cells, you can see it really here, or their impact anyway. There's a band of white cloud near the equator. It wanders around a bit with the seasons, and this is February, so it was wandered around a little bit. But you can certainly see the impact of the Hadley cells, because the equator is quite green, isn't it, under those bands of clouds. There's rainforest in South America and across through Africa near the equator. This is where there's rising motion, the air rains out, and the moisture leaves the air as it rises. Now, you can also see the effect of the Hadley cells where they come down again at the end of the Hadley cells, because that's when the air, which is now dried out through rain, is descending, and it's pretty clear that there's some deserts. The Sahara is impossible to miss in this image, but there's also drier, sort of more deserty land in the southern hemisphere at a similar latitude away from the equator. So this is the impact of the Hadley cells. But if you start to look here at higher latitudes, in both the northern hemisphere, in Europe maybe, and across the North Atlantic, and in the southern hemisphere as well, you can see that the motion looks different. In fact, it's rather swirly. The clouds are in a spiral pattern, and this here is a low pressure system, and there's another low pressure system here. These are cyclonic systems, weather systems. So this is what I was talking about. This is where the feral cell is really the average activity of a lot of waves and instabilities going on. And that's what gives us our weather. So, that's a nice picture of the Earth's atmosphere. Why do we study other planets? What's I've talked about the Earth, and the importance of the Earth is clear because we live in it. We need to understand our atmosphere, but why study other planets? I think the first motivation is fairly obvious, that they're just fascinating places in their own right. I hope you like the picture of Jupiter. I certainly enjoyed that. I find that fascinating, understanding the flows, and similarly Mars, fascinating, and why it's different from the Earth. But we also want to understand things like how the solar system's evolved and life. Perhaps the Earth wasn't always the best place for life 4 billion years ago. It might well not have been. It might have been Mars then. So understanding the atmosphere is important for understanding the solar system. And then, as Nick mentioned, spacecraft exploration, operational safety. We need to understand atmospheres. It's actually becoming more important as we get more advanced with our spacecraft, because we try to push closer to the engineering envelope. We don't build in such huge margins. And so when we're pushing close to that envelope, we need to understand the density of the atmosphere we're flying through very often and what its variability is. But actually what I'd like to talk about tonight is none of those things. It's the idea of comparative planetology, which is often cited by scientists, but rarely fully explored. We certainly understand other planets by understanding a bit about the Earth, but I'd like to ask really, can we look at other planets and actually transfer something? Can we learn something that we can bring back to Earth? And I'm going to argue that there have been a few examples from Mars research that we have done. Things that we've learnt are more important on other planets, so we study them a bit more, and then actually, they turn out to happen on the Earth as well, but often to a lesser extent in the modern Earth. And also this comes back to the idea of experiments again, maybe. We're looking at things that are way outside. We're going to test our models, really stress test our models on objects that are way outside our current experience of climate on Earth. So, a few examples, and I'm going to bring, all these examples are from Mars. So how do we understand Mars? Well, these are all models that are run at the Open University now. So we have, as I was describing, a global climate model of Mars, global circulation model, and we can run it in what I like to think of as a climate mode, which is on the left. It's a global model, but it's a fairly coarse resolution picture, if you like, because we're going to run the model for a long time. We can run it in a sort of weather mode, which is the same model, but simply turned up to higher resolution, so we can't run it for so long, but we're going to look at more individual events in more detail. And then if we want to get really detailed, we have to go down to limited area models, or in this case what we call a mesoscale model, a medium scale model. And those who know a little bit about Mars might recognise why this particular model was run, because this is Gale Crater in the centre. The purple is Gale Crater, the little bit of yellow in the middle is Mount Sharp, and if you've got very good eyesight, there's a little black circle in the purple, and that is actually where the Curiosity rover landed. So all of these models are run at the OU, which we've developed over a period of time, and in collaboration with many workers at other universities as well, of course, I should say. But you also need data. It's no good having a great model, but if you don't know how to start your model off, what your initial conditions are, if you like, then what good does it do you? And another mission I've been involved with is Mars Reconnaissance Orbiter. This is the Mars Climate Sounder instrument, and this gives you an idea of this is real Mars data you're looking at. The image of Mars is just there for reference, the picture of Mars with the dust and the surface, but that is an image of Mars taken contemporaneously with this data. So the dust storms that you can see are are reflected in the data, but the data are these coloured curtains, we call them data curtains, of that are surrounding the planet. And this particular instrument flies around Mars. It orbits Mars roughly every 2 hours. So it orbits the planet about between 12 and 13 times a day, from pole to pole. And every time it passes over, it makes thermal soundings. So the colours represent temperature in the atmosphere with a much expanded vertical scale, exaggerated vertical scale, so that you can see them. And you can see there's all sorts of issues with this. That, you know, in some places the bottoms of profiles are cut off. Sometimes that's because you're going through a dusty region and they can't retrieve the temperature when the atmosphere is too dusty. Sometimes it's just because of various things that have happened on the spacecraft. It's had to do a roll or a yaw manoeuvre or something, and so it had to turn the instrument off for a while. But this is a good day. We've got about 13 orbits, and you can see that each of these curtains is drawn down. It crosses the equator. But another issue with this data, or these data, is that all this it's not a synchronous picture. It's asynchronous data. So in other words, we fly and take one data curtain, and it doesn't come back to take the next data curtain until 2 hours later. And the problem with atmospheres, unlike planetary surfaces, is that they move. And in that 2 hours in which the data in which you've been flying around the other side of the planet, that everything's moved a bit. So it's a bit like the old wagon wheels on the movie problem, where everything's aliased and you don't see things change while you're looking at them. We never really get a global picture of the planet. So how do we cope with that? Well, a technique which I've been involved in developing for the last 30 years, really, called data assimilation, which is used on the Earth for getting the initial state for a weather forecast. We use it for a slightly different purpose on Mars. So in other words, we've got our observations, which have the problems, the limited coverage, uncertainties, but nonetheless they're real data, so they're massively valuable. That's actually what the atmosphere is doing now, which is what we want to find out. And we've got the model, which is great because it's got global coverage, and we've got nice uniform sampling, but we don't know what state it should be in, what the initial state should be. And data assimilation is all about bringing those two things together, combining them in a statistical way, and eventually coming up with if you like, a model state that is most plausibly best fits the data that we've got. And that's another way of thinking about that is that we're using our knowledge of physics to interpolate between the observations. So we see something else 2 hours later, but we know that it's moving. We can work out what the winds are, and so we can make some prediction, some forecast as to how it's changed during that time. And we can combine our knowledge of physics with our simple knowledge of the observations to make something that's a bit more than the sum of the parts, or we hope. So, first example of the value of this is landing one of these rovers. This is the Curiosity rover sitting in Gale Crater. I showed you before how the Gale Crater model was embedded within the global model. So we run the global model. We wanted to land Curiosity. The problem with landing these things is it's a big beast. You often see these images on the news and it's unclear how big they are. So Curiosity won't park in a standard American parking space. We've tried it, and it takes about 1.5 parking spaces. It's like a big four-wheel drive vehicle. It weighs about a metric ton, which is heavy for a spacecraft, and you have to land safely on the surface. When it arrives at Mars, it was travelling at 21,000 miles an hour, or kilometres an hour, I think, and it has to stop in about 6 minutes. But it doesn't want to stop too soon, or you're left dangling up in the air, or stop too late, in which case you hit the surface rather hard. And so that involves knowing a detailed density profile of the atmosphere. But the problem is, on Earth, you would solve this problem by probably going and looking at some past record. You would get a weather station nearby where you were landing and go and look at the record. Unfortunately, no one's set up a weather station network on Mars, so we had to predict, or try to predict from first principles. And I'll show you some forecasts. They may be not. These are real, genuine forecasts that I made for both Curiosity and Perseverance. They're a little on the left is Curiosity, which landed in 2012, and on the right Perseverance, which landed this year. And in each case, the continuous line is the forecast. So in the case of Curiosity, it's actually a forecast for. It's not the day of landing because there wasn't any observation. The instruments weren't all turned on at that point, but we just compared after the event. The blue line here is my forecast of the surface pressure at the Curiosity site for a week. from about 9 days after landing. On the right is a forecast of surface pressure at the Perseverance site. It's a little different because I've just folded it in by time of day. So this is the black line is now an average, and the grey line is some distribution about that average of what I think the surface pressure would be over several days. And on the left, the black little bars are the actual measurements made by the Curiosity lander. On the right, the coloured dots are the actual measurements made by the Perseverance lander. And you can see we're not totally without skill. Firstly, the biggest worry was would we even get the surface pressure right, because the surface pressure on Mars varies very strongly with time of year. And we do seem to have got that nailed down, which was one of the biggest concerns. But the second thing is, how does surface pressure change with time of day? And in the case of Curiosity, it changes rather simply. The surface pressure is high early in the morning and low late in the afternoon. It falls very rapidly during the day, and the cycle repeats. It's a bit like Los Angeles. Every day is the same, or at least it is at this time of year. Perseverance is a bit more interesting. So we actually predicted this, that we would get a high pressure at 8 o'clock in the morning, but we get another high pressure at 8 o'clock in the evening. If you think about this, you might understand, are you familiar with something that's high twice a day? Well, it's a tide. It's actually a thermal tide, though. It's not a gravitational tide. It's a thermal tide from the sun going around. But the fact that we were able to relatively, well, it's not perfect, certainly. I wouldn't claim perfection, but we got the right phase and amplitude, I would say, of the main components of the tides right for each site. Kind of is quite satisfying. The other aspect of these forecasts is they were both made about 2 to 4 years before the landings happened. So they're quite long-range forecasts. These are really climatology forecasts. They're climate forecasts, not weather forecasts. But there wasn't a lot of weather, certainly not at the Curiosity site. On the other hand, then you could argue where we predicted there wouldn't be a lot of weather. So there's a bit more weather going on at Perseverance. That's one of the reasons why the fit isn't perfect. There are, but there's not a lot. They're both quite near the equator. Okay, the next topic I'd just like to talk about is Mars weather. We've talked a bit about weather systems. This again is a visualization from our global circulation model at the OU, and the colour scale, which the label hasn't come out, unfortunately. The colour scale is water ice clouds, and the little vectors give you an idea of winds. And actually, what you're looking at here is this is winter time in the northern hemisphere on Mars, and you're seeing a jet stream around the pole, very familiar to us from Earth. And in fact, the jet stream splits in this example. You can see where a puff of cloud towards the centre of the image has come off more towards the equator, and that's a splitting jet stream is a classic phenomenon in terrestrial meteorology as well. So just like the Earth, there's a winter jet stream, and there are waves that go around this jet stream. I'll show you some of the waves now. This is now a real image of Mars. It's in the spring. It's not the winter, because you can see the North Pole. So it's just the North Pole has just lit up in the spring, and what the white towards the top is the polar ice cap. But I think you can see, hopefully, pretty clearly actually, there's a spiral system here. There's another puff of dust here. This is all dust. You can see there's not much cloud. There's a little cloud over on this side, but this is all of this stuff that looks like cloud is actually dust that's been thrown up. So that's what's showing you the weather. But there's certainly a cyclonic low pressure system here. And in fact, if you look very closely, you might see over here an arc of a weather front, again shown up by dust, which stretches over the edge of the polar cap. Now we can run our model for the same time as this, and here's it won't look immediately like it because I'm showing you air temperatures in our global model, but it's from the same time as this image, and what you can hopefully see here is that it's not simply warmer at the equator and colder at the pole. There's something going on, and that something, I would suggest, is that warm air is coming up, it's being drawn up this way, and cold air is being pushed down this way from the pole. And in fact, this triangular pattern is very familiar to a terrestrial meteorologist. It's called a warm sector, and this is exactly what's happening. A low pressure system is up here, and these are weather fronts. Here's a cold front forming. Our model can't quite resolve a cold front because it's got a limited resolution, but quite a good resolution in this. It's run at weather resolution. So there's a cold front happening down here and a warm front here. And in fact, where I've put the laser pointer now, is pretty much exactly where we're sitting, or would be sitting, right now. We're in a warm sector tonight. In fact, the warm front passed over us very early this morning. There's a cold front sitting up in northern England right now, near the Scottish border, and it's going to push down over us tonight. Tomorrow morning, sorry, it will reach Milton Keynes tomorrow morning, around sometime before lunchtime. So sometime before lunchtime tomorrow, we're going to get a band of rain come down, which is associated with this air being pushed together at the front, the cold air being pushed down. So this is a very terrestrial-like situation. In fact, back to understanding the weather, here's the picture from the classic Earth. If you do Earth meteorology, this is a classic low-pressure system over the North Atlantic that everybody will learn about from the Norwegian School of Meteorology through to the modern day. And this is the warm sector, cold air, a cold front here. There's the warm sector in that triangle, and warm air being pushed and drawn that way. And that front there is what you could see delineated by dust in the image of Mars. On to something a little bit more complicated, if I've got time, I think. This is something from a paper I published with colleagues in 2016, and it's quite a complicated figure. So I won't have time to explain it all, but I'll try to explain the main features. So what you're looking at here is, if you like, a map of storminess, and where it's red, there's a lot of weather going on. There's a lot of highs and lows passing over the location. Where it's green, it's quite calm. The weather's the same every day, if you like. It's a bit like Curiosity. And this is the North Pole. This is the South Pole. There's not much weather at the equator. And this is time along this axis for several years. We've reconstructed the Mars weather for several years. The Mars years are all numbered now for convenience. It's not an international system yet, but this is Mars years 24 to 26. A Mars year is about 2 Earth years long, so it's quite a lot of data. And so if we just focus on the northern hemisphere, where we are up at about 50 degrees, let's put on a few boxes to draw your attention here to mid-latitudes. So just look at these mid-latitudes. This is autumn. This is where we are right now. That would have been September the 21st in Earth units there. And so we're sitting about here now. And this is where all the storms happen. So the storms come south from the polar cap as the polar jet stream comes southwards. But then something rather unexpected happens. We would expect, certainly higher in the atmosphere, this does happen. The storms just get stronger and stronger, and they're strongest in the middle of winter, which is when the temperature gradient is the largest. That's what you'd expect. And then they die away again in the spring. But down near the surface, this is only 2 kilometres above the ground. This is what the weather you'd be experiencing if you were on the surface of Mars. In fact, something rather bizarre happens. All the big storms happen during the autumn. They build up, and then they sort of calm down right in the middle of winter. So this would be Christmas time on Earth, the winter solstice. So the middle of this box is, if you like, late December on Earth. And or the equivalent. And so this was a rather remarkable feature that's very strongly apparent in this data set, which models didn't produce until I had done this reanalysis, this combination of data with models. And it's become known, now as the solstitial pause, it's known on Mars that dust storms are slightly less common at this time because the weather is less active. And rather intriguingly, the idea has come back to Earth, and there are just hints. It's not so strong as this example. There are just hints that actually this happens on Earth too, that you get the strongest storms happen in the autumn and in the spring, or early spring, but don't happen right in the middle of winter. You tend to get quite calm weather on Christmas Day, if you like. Think of it that way. And the same thing happens to a much weaker extent in the southern hemisphere. I haven't got time to discuss why now, but the same sort of phenomenon seems to happen. So there's a phenomenon that we discovered on Mars because it's much stronger, but actually people have come back, and you can see this in the North Pacific weather on Earth, apparently. Next, dust. Mars is all about dust storms. This is actually a pretty small dust storm. You can see it's moving from right to left across one of the northern plains on Mars. Dust is a major driver in the Mars climate. This is some work done by a recent PhD student, Paul Streeter, and myself. People have been interested in Mars since the in Mars dust since the late 60s. It's a constant mystery why you sometimes get dust storms and you don't always get them, and what impact they have. And dust is obviously a massive factor for the climate. It's well known, I think, that if you have plenty of dust in the atmosphere, less sunlight will get through to the surface, and the surface will be cooler during the day. That seems fairly self-evident. This is the old nuclear winter idea that people used to worry about for the Earth. But actually at night, something different happens, and it's a bit like having a cloudy night on Earth. If you have a cloudy night, you tend to not get a frost in the morning, because the infrared radiation sent up from the surface, as the surface cools, is instead scattered in all directions by the dust, and some of it's scattered back down to the ground, and it actually keeps the ground a bit warmer than it would be if the dust wasn't there. It's a sort of greenhouse effect. And actually the net effect of the two in this state, comparing a dustier year with a less dusty year that Paul ran, shows you this complex pattern, but certainly some places on Mars are much warmer when there's dust near the surface than they would be without the dust, and some places are cooler. So Mars has a complicated greenhouse effect. And on Earth, dust storms are important now, but they tended to be less modelled because Earth's climate is so dominated by clouds, water ice clouds, whereas on Mars, water ice clouds are less relevant. I'll just show you the Mars, a storm developing in our Mars model. So a little orientation guide first. This is a little map of Mars for those who are not familiar with the planet. This is a standard sort of equal angle map. So the northern hemisphere of Mars is, don't worry about the names, but the northern hemisphere of Mars is essentially flat, and it's a big plain, the various planitia plains. The southern hemisphere, on the other hand, is a warm colour, and that means it's high and rocky, it's rough, and some of the most dominant features, of course, are the giant volcanoes. Olympus Mons, 3 times the height of Mount Everest, and the footprint of that volcano is the size of France, which is quite big for a volcano, if you think, especially on a small planet. Tharsis Ridge, 3 volcanoes along here, and a volcano on the other side of the planet, the Elysium Montes. So that just gives you a little orientation guide to what you're going to be seeing. So we're now going to, because the movie was shot from a different angle, we're going to turn the map upside down and rotate it a bit of an angle. And so we're looking down from the north now. So you look out for Olympus Mons on the right and the Tharsis Ridge here, and then Elysium this way. So hopefully the movie will work. And this is showing the beginning of a dust storm, which actually a global dust storm, which started in 2018 in our model. And don't let me down now, please. It worked in practice. That is just typical, isn't it? Why did it work just before the talk? Here we go. Okay, I've managed to do it with the key. So you can see the dust. So the surface is this is actually the dust in our model being blown around with an exaggerated vertical height scale. Here is Olympus Mons, the giant volcano. It's an exaggerated vertical height scale. It would actually be rather flat because it's got such a large footprint. But you can see the dust blowing around. And one thing you might well be able to see is that the way it seems to slosh around, and that sloshing is the thermal tide. That's that's the sun moving from left to right. But now you'll see a dust storm really kicking off in the Tharsis region, the dust being lifted up every day when the combination of the thermal tide. And this is, if you like, a 3-dimensional, 4-dimensional reconstruction of a real dust storm on Mars that we can run in our model. Okay. Well, I said dust's important on Earth too, and I'll just give you an example. This is actually an image it's not hard to find a dust storm on Earth, actually. This, you may be familiar with finding dust on your car or your windows sometimes and it's always said to be from the Sahara. Well, it often is. And this is a fantastic example. This is actually an image of the Earth from June this year, from the 16th of June. And I will show you the dust storm. It's in this region. We'll blow it up a little bit. There's the Sahara. You can see the sort of rather sickly yellow colour, orange colour. It's the dust being blown off it, and it's being blown all the way to Central America. It's actually raining out in the Caribbean and in Central America. So, planetary scale dust storms happening right now. Well, a few months ago anyway. And so, understanding dust storms is important. For the present day Earth atmosphere, it's clearly, even in this image, dominated by clouds. but it nonetheless plays a role, and we've improved our understanding of dust on Earth through looking at Mars. Dust has probably also been more important in the past than the Earth as well. Okay, I'll move on to our next topic now, which is about climate history. These are dry riverbeds on Mars, but they're not recently dry. They were probably dried up about 4 billion years ago. It's an incredibly ancient surface. So we know Mars was a lot warmer and wetter than it was now, because you don't get riverbeds like this without rain. Nowadays Mars is dry, but you still see ice. This is actually an image taken by an instrument called Cassis on the ExoMars Trace Gas Orbiter. Oops, why does it sometimes go into automatic? Anyway, so this is an image taken by an instrument that is actually co-managed at the Open University. So some of the people who choose the images it takes are sitting in the audience now, I think. And this is Korolev crater in the northern hemisphere of Mars, and the winds here have brought a frost down from the northern polar caps. So this white water ice doesn't sit there all year. It's just been brought down by the winds now. Very thin layer of frost. Bit more. Bit larger region of aqueous alteration. This is an example from a PhD project that I'm running at the moment with no U student Laurie and Foley. And this is Leo crater. It's a huge crater in the northern hemisphere of Mars. But there's lots of signs, an image on the left, there's lots of signs if you're a geomorphologist that there's been various aqueous alteration in the past in this crater. So we've actually zoomed in our limited area model. We're measuring where the ice is accumulating. And now the great thing is, with our model, we can play games that we can't play in real life. We can look back in history. So we can go back to previous times on Mars when the climate was different. We can change the orbital parameters of Mars and see if things changed, and can we understand how these features have formed over the history of Mars. So that's another thing we can do with a model. There's no surfaces as ancient as these riverbeds on Earth, I should say. Mars preserves features that are much more ancient because of the activity on the Earth. And then finally, looking again at the global scale, so this is going back to this dust storm you saw. This is some images prepared in collaboration with James Holmes. And on the left is the sort of state just before that dust storm you saw. So there's the dust over the planet Mars. We're in the south now, so the southern hemisphere is towards us. And on the right, we've put some other features of the model. So the blue is the water vapour in the atmosphere, and the pink is the water ice clouds. There are a few clouds, just as you saw in the image of Mars way back near the start of the talk, and lower clouds over the poles. But this is a sort of typical state when Mars is a bit dusty, but not very dusty. And only a week later, this happens. So there's the dust storm blows up. Maybe I can talk backwards and forwards, and you'll see the impact of the dust storm on the water. So the dust storm's just kicked up here in the Tharsis region, and the water has been blown much higher in the atmosphere. The atmosphere's warmed up, there's fewer clouds, water's transported much higher. Why is that significant? Well, if water's transported high in the atmosphere, it gets broken down by photochemical reactions to its constituent atoms, and they escape to space. And so maybe understanding the escape rate from these sort of processes, the role of dust storms in escape, is what is a key to understanding the history of Mars. How did Mars dry out so much? We still don't fully know, but certainly a large amount of water has probably escaped to space, and we're trying to work out now how fast it's escaping and what's governing it. And it seems that dust storms are maybe a key to the escape rate. So I'm just going to finish now with this image. I was rather struck by this image. It actually was taken by a camera that is mounted on a Mars spacecraft, but it was taken from Mars, and the camera is for looking at the surface in high resolution, but it was turned back on Earth at some point, and this camera would have roughly the power of a really top-of-the-range amateur telescope. So the sort of telescope that if you're a really keen amateur astronomer, you might have in your back garden. So if you were a Martian astronomer, this is the view of the Earth. So that we can actually see you can certainly see we've got clouds. It's straight out of H.G. Wells' War of the Worlds, if somebody was sitting on Mars now, they could see us. They could see we were different from the Moon. Certainly, you can see the Moon in the top right. And I hope that gives a little perspective on one reason why you do planetary science, because you gain a different perspective on the Earth than you have looking from below only. So, with that, I would like to thank you for your attention.
Thank you very much, Stephen. We're going to go over there in just a moment, or you can set off now and I'll join you. Just to say we're going to hear questions from people in the lecture theatre, if you like. We're not going to use the microphone, so if you just speak clearly and loudly, I will relay it through my microphone to people online. People online, if you'd like to send them in by email to the address which is there on screen, it'll then be relayed by voice back to me and I'll try and repeat it. So that's what we're going to do. It would be good if you could identify yourself by name. Makes it feel a bit more friendly. Say who you are. And have you got a question for us right at the beginning, Helen, from online?
Yeah, I have from online. It's from somebody called Alex Wood. He's got two questions. You mentioned the large physical model in a spinning tank is still useful. At the current rate of progress, how long until our computer models can achieve the same small resolution over the same large scale?
Okay, first of all, can I just repeat it? It's essentially comparing the analogue computer of the big tank experiment and the numerical models that Stephen does before breakfast.
Yeah, well, and after breakfast, I have to say. It's a very difficult question, because when do you really... And I think actually we'll always want the real fluid experiments, because we always want to validate and test our models. How do we... It's a very dangerous situation to get into, where you believe one model and you believe that's reality. I'm certainly a modeler and I love my models, but I would still like to test them against reality occasionally. So that's one factor. We're still well away from getting the full range of scales. So to give you an example, on the whole planet, if you like, we can resolve down to, with a single model, we can probably resolve down to scales of several kilometres with a global model of the Earth, with the very large computer clusters. But remember that real viscosity doesn't happen in air till you're on a scale of about 1 millimetre. So we still have this whole grey area between the tiny motions at 1 millimetre and the motions out at several kilometres. And that grey area is a large part of the complications that are in these models. How do you describe the effect of the small scale that we know about? We know how viscosity works in fluids on tiny scales to the large scale. So good examples of that are extreme weather events, which are often, in the past, haven't been forecast very well. So I'm thinking of something like the Camelford floods in Cornwall, for example, where they didn't capture the full extent of the intensity of the rain, because the model simply couldn't go down to a small enough scale. So I think there's always going to be a place for these for looking at reality as well as looking at models, but we're still well away from just thinking that computing models can do everything. We shouldn't think that.
It's not just rotating tanks, but presumably it's rotating the Earth as well and using that as the model. And your other planets are your experiment.
And other planets, exactly. So we're a million miles away from ever being able to simulate Jupiter, which is a vaster range of scales than the Earth. So I said several Earths could fit inside the Great Red Spot. Well, Jupiter moves and thrashes around on small scales just like the Earth, but then it's 10 times bigger, effectively. So.
Thank you. He has a second question. You mentioned that our weather forecast accuracy is extending by 1 day per decade. How long do you think that rate of progress will continue, and are there theoretical limits?
So this is the forecast, the one day per decade improvement. How long can we go on, Stephen?
Well, I'm not sure I can say precisely. I think we're probably starting to level off now. It's not that we can't carry on improving, but improvement gets harder and harder and harder. So the tiniest famously the whole idea of chaotic systems. The tiniest change in the initial conditions grows exponentially with time, so that if you like, buying a day into the future is progressively more and more expensive. I don't think computing power at the moment the computing power is not increasing at the rate it was actually, the Moore's law, so the computers aren't getting that much more powerful, but more importantly, we've actually improved our observing system so much. So in the past, the big flaw was that we perhaps had lots of observations in, let's say, northwestern Europe, where there's a lot of people, a lot of money as well, and weather stations. Very few observations in Africa. But that sort of ballpark has been levelled a lot by the coverage from satellites. So as we have more and more satellites, the difference between northern and southern hemisphere of the planet has been evened up. And the southern hemisphere forecast was pretty bad a few years ago, and it's now, a few decades ago certainly, but it's now caught up rapidly with the northern hemisphere forecast, but of course that will tend to even out as we use satellites more and rely on individual people and weather reports less.
Okay, thank you very much. Question in the room. I see one from Jan Zanecki.
Hi.
Hi.
Thank you very much, Stephen. Fascinating talk. Exoplanets. We know, 5,000 or so planets beyond our own solar system. Do you expect in your lifetime that you'll be studying weather on some of those exoplanets, or is that fanciful too?
Weather, I don't know. Climate, yes, because we do that already. We've done that already. We've modelled hot Jupiters, large Jupiter-sized planets near stars with different rotation rates. So we can do that in the broadest sense.
Them, but can you measure?
At the moment, you can't measure very well. No, you can measure only the simplest, broadest, large-scale parameters. So yes, you can't validate the models in the way I'm comfortable with an Earth model. We should always be humble in the face of how complex these systems are. I talked about Venus, the difference between Venus and Titan actually, and Earth and Mars. Earth and Mars are rapidly rotating planets, and they have similar weather dynamics. Venus and Titan are slow rotators, and their atmospheres super-rotate massively. Well, if we didn't know they super-rotated massively, until a few years ago, we wouldn't have been able to predict that with models. Models don't reproduce superrotation that well, and we've made a lot of advances on that. But I would argue that we would never, had we never seen Venus, we would have a very bad idea of what its circulation is, actually. Or at least we wouldn't know we were wrong for a long time.
Okay, I have another question down here from online.
Yep. Has the study of atmospheres on other planets made you more anxious about climate change on Earth because of the fragility of our atmosphere?
Can I just say, this is a very good question. This is, of course, COP26 that we're in the middle of, and worrying about the fragility of our atmosphere based on insights that you gave from space, Stephen.
Yes, I think the simple answer is yes. I mean, I've been well aware of climate issues since the 80s when I started working in this field. It's obvious that I'm a planetary scientist. I talk to Earth scientists a great deal of the time, and it is a concern. And it's I wouldn't say I wouldn't go into the total doom and gloom scenario of thinking, well, we're going to end up like Venus in a runaway greenhouse where the oceans have boiled, if there were any oceans, and the planet is hot enough to melt lead on the surface. Actually, maybe we will end up like Venus, but probably not for 1 billion years. That's not human climate change. That's way outside that scope. But it does show you the vast range of parameters, if you like, that atmospheres can settle over it. There's no reason why a planet should be as accommodating and as nice as the Earth. It's just, well, whether you regard it as luck or how you want to regard that. We've evolved to enjoy the climate we've got, and the fact is that no other, had the Earth had a slightly different climate, we have a natural greenhouse effect of about 33 degrees. If we didn't have that natural greenhouse effect, we would be frozen. There probably wouldn't be life on Earth. If we have a greenhouse effect a bit more, we could push over the edge, and various drastic effects could happen. So yes, I'm certainly well aware. I don't think we should panic, but equally, I don't think we should sit back and think, well, it's always going to be okay. We're in this. I'm certainly well aware of how thin how thin a skin we live in. It's always quite interesting to remember that if you went 5 kilometres that way, you probably couldn't survive, and if you went a kilometre or 2 that way, you couldn't survive. And it's not very far in the scale of the universe.
I shall never eat an apple and feel the same again.
No.
Any other question from the room? Not, I'll give you online one more chance if we've got another. Oh yes, please.
You mentioned about Mars drying out.
Mm-hmm.
How close are we to understanding why it's drying out, or how it dried out, should say?
I'll just repeat it. This is the loss of water from Mars.
Yeah.
Yeah.
How close are we to understanding all of that?
Well, it's certainly a topic that many people are working on very hard. We know, I mean, I suppose, what do we know? We know it was wetter than it is now. But we're talking a long time ago, 4 billion years, 4.5 billion years, the planet's formed. The sun formed about 4.6 billion years ago. The planet's formed about 4.5 billion years ago. We're talking within the first 500 million years. So this is incredibly far back in time. There's nothing that old that we can find on the surface of the Earth, for example. It's all been churned around a lot more since then. So it's not an easy problem. It's deep time. We know that Mars was wet. I think we can be pretty confident that it had precipitation of some kind, whether that was snow or rain. I can't swear to, but I suspect it was both. We know that Mars went through a phase of being much more icy, but there were still mega floods. There's signatures of mega floods all over the surface where the ice has broken and washed away features. We then, and that was up to about 3.5 billion years ago, and then we know that for the last 3 billion years, Mars has been, well, it's varied. Its climate has changed, but it's not changed to that extent. It's varied between different states. So we know that there's been this big change. Why is a question that many would like to answer, and how it actually got from one to the other. But it's a big challenge. I think the story I would give you is something along the lines of, we know that Mars had a magnetic field in the past, and that magnetic field is really only fossilised now. There's no active, the active magnetic field is almost gone. Now, is it the case that the magnetic field stopped for some reason and was disrupted, and when the magnetic field stopped, the atmosphere was less protected, and so all this water that was being transported into the upper atmosphere, the wind? Well, that's certainly part of the story, but there's a chicken and egg here, because was it the case that the water, if you like, the magnetic field stopped because the water stopped? Mars doesn't have active plate tectonics in the same way as the Earth does. It doesn't have moving plates anyway. So it's a very different planet, and I think the answer is we're gradually piecing it together, and missions like the upper atmosphere satellite MAVEN that's operating now, and our sort of studies of the lower and middle atmosphere, trying to tie together and trying to work out what the loss rate is. If we can pin down what the water loss rate is now and in the recent past, and the recent past might be 3 billion years, it's quite, then maybe we can have a better estimate. You know, there's probably a lot of water under the surface of Mars as well. We know there's a lot of ice under the surface, so water's sunk down. We could expect there to have been a 500 metre deep sea in the northern hemisphere of Mars in the past, just on the basis of thinking, well, it's probably about like the Earth, it's not that different in terms of composition. So that's a long answer. The short answer is we don't. I wouldn't say I know, but there's lots of ideas, and it's probably connected with a series of catastrophic events which were to do with the atmosphere cooling. Probably the atmosphere lost a lot of mass. The atmosphere was probably a much thicker atmosphere in the past, because it would have to have been to have liquid water exposed to the surface. If you expose water on the surface of Mars now, it would rapidly freeze and then sublimate. You won't have liquid water. So the answer is something pretty bad happened, but it's hard to say what at the moment still. But it's an interesting question.
Good. I think we've taken one more, have we?
Yeah.
Helen,
So there's some comments about it being a fantastic talk, but there is one more question online from Dr. Liz Carvin from the School of Physical Sciences here. So you've talked about morning and evening, spring and summer, and so on. But each planet has a different year length and day length, and in some cases the axis of the planet has a different orientation. how does this affect the prediction of weather on different planets?
So that's the relationship between the planetary cycles of day and night and years and so on, and weather.
So one of the reasons I talked quite a bit about Mars is probably because in those respects Mars is the most like Earth. Its year is almost twice as long as the Earth's, but actually Mars is tilted with respect to its orbit around the Sun by almost the same angle as the Earth is currently, and that means you get the same sort of pattern of spring, summer, autumn, winter. And also Mars rotates only a bit slower than the Earth. It's a day on Mars, a solar day on Mars is about 24 hours and 40 minutes in our time. This is a great problem if you work on a Mars mission, actually, because I know a lot of colleagues in JPL in California who drive these rovers are driven mad because they basically have an app and work on Mars time. And of course, if you're slipping 40 minutes every day, it does horrors to your body clock. But nonetheless, Mars is very similar to the Earth. It rotates for the same sort of period. A day's about the same length. It has the same pattern of seasons. Other planets are different. So Jupiter, for example, rotates very fast. It rotates with a 9-hour period, but also it's sitting almost upright, so it doesn't really have seasons. It's kind of, if you like, spring all the time. Same on Venus, actually. Venus is sitting almost upright, but it rotates very slowly. Venus has a very strange situation where it rotates the other way. Well, depending on which way you look at it, you can either say it rotates backwards or it's upside down. It doesn't matter which view you take, but it rotates the opposite way to all the other planets. But it also rotates very slowly. So a day on Venus, a solar day, is very different from a rotation period. On Earth, we talk about a day quite casually. There are different sorts of days. There's a rotation period of the planet, and there's also a solar day, which is when the sun is the same position in the sky. And they're about 4 minutes different on Earth. 24 hours is actually a solar day. The Earth rotates a bit faster than that. But on Venus, they're hugely different. So it's a very strange place. If you were walking on the surface of Venus, not that I'd recommend it, you could keep up with the same local time of day, pretty much as you walked around the planet. So that's kind of the day moves around the planet at that sort of speed. So yeah, in each case, and that's part of testing the models. So if you like, if I go back to my tank in the laboratory, what do I want to do? Well, I want to spin it twice as fast, or I want to spin it half as fast. And that's exactly what the planets give you. Systems that rotate at slightly different rates.
Okay, thank you very much. I think we're going to let Stephen off at that point, and I'm going to walk over here and at the same time say, Stephen, that was an absolutely fabulous lecture. I have never understood the weather, even when we were writing a course of that title itself, quite so well as I do for having spoken to you this evening. So I thank you very much for that, Stephen. Now, we do strive for continuous improvement, and so feedback is always welcome. There are some feedback forms for people in the room. If you've been watching online, we're very happy to receive your comments by email, of course. I'd like to thank everyone for joining us this evening, whether or not it's been online or it's been here in the room. And for those who are in the room, there is a treat downstairs that we can go to in just a moment. But before that, I'd like to leave you with details of the next inaugural lecture event on the theme of children and migration as brokers of care. This will take place on Tuesday the 30th of November at 6 p.m. and will be delivered by Sarah Crafter, Professor in Cultural Development Psychology in the School of Psychology and Counselling in the OU's Faculty of Arts and Social Sciences. And it will look at young people's migration experiences. Details are available on the Open University Research website, and we've got a little trailer, I think, just to tease you with at the end.
The transition to adulthood holds particular challenges for children of migration. In my inaugural lecture, I will bring some of those challenges to life using examples from my own research with child language brokers who translate and interpret for family and friends, and lone child migrants, children migrating without kin. I will draw on the concepts of care and critical childhood to show how anti-immigration contexts frame children's lived experience.
Well, there we are. Come back on the 30th if you want to see that, and I guess that will be streamed as well. So, thank you very much. Have a good evening.